I remember when I first got married, my husband and I would go visit my mother-in-law and my father-in-law. And we would do lots of stuff. We'd cook, we'd clean, we'd straighten up the house, we'd take them out to eat. But every day at 11 o'clock, the house would come to a standstill because mom and dad had to sit down to watch The Price is Right. I mean, they would like talk to the screen and yell out the prices and cheer for people that they never knew. But there was always one game that brought a hush over the entire living room, and that was Plinko. Now, Plinko is a game of complete unpredictability, right? A contestant drops a circular disc into the Plinko chamber, watches it bounce from left to right off of these tiny pegs until it finally hits the bottom, hopefully winning them a lot of money. But little did I know at the time, what I was actually witnessing was the normal distribution in action. Now, in the game of Plinko, if we were to add up the sums of the right and the left bounces, we'd see that they follow a normal distribution. Now, the normal distribution is one of the most common, well-used distributions in all of statistics. Normal distributions have come in lots of means and standard deviations, but they all have that same signature shape, where the data values, they fall on a smooth bell curve. Now, here we see a sampling of curves that follow the normal distribution. Notice a couple things. They've all got that bell shape. Right? And the data appears to be really concentrated in the center, but some of them are more spread out than others. In fact, let me draw your attention to these two distributions. Right? Both of them are centered at 15, but they've got slightly different standard deviations. One you see here has a standard deviation of 7, and the other one here has a standard deviation of 2. Now notice that the spread of the distribution is going to be determined by what that standard deviation is. Right? So if my standard deviation is 100, you can imagine that my distribution is going to be way spread out. Now, every normal distribution has certain properties that are going to directly help us characterize it. Here's the first one. The shape of the distribution is symmetric, meaning if you were to cut this distribution in half, the left side would be a mirror image of the right side. You could fold it and they would overlap each other perfectly. Secondly, the bulk of the probability is toward the middle of the distribution, right? So you see the bulk here in the middle, and then it's going to decrease toward the tails as we move out from the distribution. Third property, the mean, the median, and the mode are all the same, and we can find them right smack dab in the center of our distribution. Now, why is the normal distribution the most common distribution in statistics? Well, here's why. It's because normal distributions approximate so many of the natural phenomena that we see around us. And in fact, it's become the gold standard for probability problems. Now, many of the variables that we observe in everyday life, like heights and weights, shoe sizes, reading ability, measurement error, they're all approximately normally distributed. And even some of the discrete variables that we've talked about before, like the binomial, we can actually approximate them with a normal distribution. Now, by definition, a continuous random variable x has a normal distribution with a mean mu and a standard deviation of sigma if the probability density function looks like this. F of x equals 1 over sigma times the square root of 2 pi, e to the minus x minus mu quantity squared, all over 2 sigma squared, as x goes from minus infinity to infinity. Now for shorthand, rewrite x with a tilde, which means is distributed as a normal mean mu standard deviation sigma. All right, I can see your face right now. And I'm even reading your mind a little bit. And so I'm sensing that you're thinking, where in the world did that equation come from? Well, we're going to go through this together, but just a couple of things to highlight. You see that 1 over square root of 2 pi? That's just a constant. And what that constant is helping us do is to make sure that when we take the integral, it gets to 1. So that's going to simplify when we look at the standard normal. The same formula you see here is used to create the different examples of normal distributions that you see here. So look closely at two of these curves. Here's one with a mean of 15 and a standard deviation of 7. If we plug those values into our PDF, right? So plug in 15 for mu, plug in standard deviation of 7, and what do you get for that? That is what the shape of that curve is. We can use the curve command to plot the normal density, d norm, at a series of x values with a mean of 15 and a standard deviation of 7. Now here we set the limit for our x-axis, which is going to range from minus 20 to 30. And the limit for our y-axis, well, that's going to range from 0 to 0.4. And the color of the plot is red with a line of width 3. In the same manner, if we take the mean at minus 2 and the standard deviation at 3, here's the shape of the normal distribution that we get for that curve. In fact, okay, what about this? You just pick your favorite number, your favorite positive, your favorite negative number, whatever it is, pick it, and then we're going to call that the mean. And then I want you to take your favorite positive number and let's call that the standard deviation. We can take your two values, plug it into our PDF, and you're going to get your very own, one-of-a-kind, normal distribution. But now, because we've got so many possibilities, we really need a common way to describe them, right? We can have an infinite number of normal distributions. So the true gold standard that we could use to solve problems, regardless of different means and standard deviations, is going to be to standardize. We're going to work with what we call the standard normal distribution. Here's what the mean and variance are defined as. When mu is equal to 0 and sigma equals 1, the normal probability distribution function reduces to a standard normal. F of x equals 1 over the square root of 2 pi e to the minus x squared over 2, where x is again between minus infinity and infinity. Now notice here, this equation, it looks a lot nicer. You're probably upset that I didn't start with it. I know. But I wanted you to see how we got there. We got there by centering our distribution at a mean of 0 and giving it a standard deviation of 1. Again, that 1 over square root of 2 pi is a constant. So when we integrate that, we're just integrating an exponential function. So rather than directly solving a problem where x is normal mu sigma, we can use an indirect approach. Here's what we're going to do, right? So we've got our data set. We're going to recenter it to have a mean of 0, right? So imagine our data centered at mu, and now we're going to subtract mu from all of our data values to give us a mean of 0. So that's the first step, recenter. The second step, we're going to rescale, right? So we've got now our distribution is centered at the mean, mu. We're going to divide by the standard deviation. So when we divide out by the standard deviation, that's going to give us a standard deviation of 1 for x minus mu all over sigma. Now the resulting distribution is denoted by z. And z follows a normal distribution with a mean of 0 and a standard deviation of 1. Okay? In other words, if x is normal mu sigma, then z, which is x minus mu over sigma, is normal 0, 1. Right? We've taken our distribution x, shifted it over, subtracted mu, divided by sigma to get a standard normal. Now, every random normal variable can be transformed into a standard normal random variable, which we call standardizing. And we do this by subtracting the mean and dividing out by the standard deviation. But what's the point? What are we going to gain when we do that? Well, Z now actually represents the number of standard deviations our random variable X has, how many has fallen, say, above or below its mean. So here's what I mean. If Z is positive, then the corresponding value of X is going to be above the mean, right? And if Z is negative, my corresponding value of X is going to be below the mean. If we have a standard normal random variable Z, we can get back to X, sort of like reverse standardize, by doing the following. Setting X equal to mu plus sigma times Z. So we can go back and forth between a standard normal and a regular normal distribution. Now, did you know that the normal probability distribution was first introduced in 1733 by a French mathematician? His name was Abraham de Moivre. And he sort of found it out by accident. I remember when I read this and I thought, how do you find the normal distribution by accident? Like, how do you just, come up with this fundamental thing to all of statistics? But here's how it happened. And I'll just confess, the best thing that I've ever done by accident is drop my iPhone at a gas station when I was talking to my mom. And it happened to be 32 days before my warranty expired. But that's the best accident I've ever had. But de Moivre, he was trying to approximate the binomial probability distribution. So he's here working with the binomial, trying to get an approximation, and lo and behold, it leads him to the normal distribution. I mean, talk about hitting the statistical jackpot. His discovery is the basis for much of what we're learning throughout this course. And not only that, so much of probability, our probability theory, statistical inference, even things like regression and time series analysis is built on this underlying formal normal distribution. So how cool is it that we get a chance to connect to that deep mathematical history? Let's talk about now the cumulative distribution function for normal. Remember, this is the probability that X is less than or equal to A. Now, since our X values for the normal can go from minus infinity to infinity, we have to integrate all the way up from minus infinity to A of our PDF to get that cumulative distribution function. Now, unfortunately, there's not a closed form of the CDF. So that means there's no way for us to actually calculate that interval by hand. We actually have to do it numerically. And if we were solving it by hand, what we'd have to do is first standardize our random variable and then use a standard normal distribution table. You see these all the time in the back of a statistics book. You'd have to look up the probabilities on those tables. But here's what I want to teach you. I want to show you how R does all the heavy lifting for you in a quick, just a couple letters, and you get those values out. R does it by using the function p norm. So p norm of A gives us the probability that Z is less than or equal to A for a standard normal distribution. And it doesn't just work for standard normals. I mean, we can plug in any normal distribution with a mean mu and a standard deviation of sigma, and it's going to give us the probability that that particular random variable X is less than or equal to A. All right, let's do an example. Suppose we've got X that comes from a normal distribution. It's got a mean of 50 and a standard deviation of 10. How do we find the probability that X is less than or equal to 45 in R? All right, so now we're going to use our p norm function. Our A is equal to 45, our mean is 50, and our standard deviation is 10. Bam! 0.308. Thank you, R, for doing all that work for me. We don't even have to stop there. What's the probability that X is greater than or equal to 60? Well, now we got to use it in a slightly different way, right? So the p norm function assumes that our lower tail is equal to true, right? We're doing a distribution out through the lower tail. But in this case, we actually want the upper tail probability because we want X greater than or equal to 60. So with NP norm, you can specify that the lower dot tail is equal to false. Here's how we do that. P-norm of 60, mean of 50, standard deviation of 10, lower dot tail equal to false. And that gives us a little over 15%. Now again, lower dot tail equals true means that we're going to return the probability contained in the lower tail, the left tail, right? So this is the probability that x is less than or equal to a. If we set lower dot tail equal to false, we return the probability in the upper tail, right? The right end, the probability that we're greater than or equal to a. Okay, what about this one? Can you find the probability that x is between 45 and 60? Again, we're going to use p-norm to calculate this probability. So now we have to subtract the probability of those endpoints. So p-norm of 60 minus p-norm of 45 with the corresponding means and standard deviations. That gives us a probability of about 53%. Now, what's fascinating about the standard normal is that as soon as you know how many standard deviations you are away from the center, you know how much of your data is contained in that distribution. Look at this graph. So the probability that a random variable falls within plus or minus 1 standard deviations of its mean is 68%. And that's not just true for the standard normal, that's true for any normal distribution. And we'll see that in an example in a second. What about within 2 standard deviations? How much data does that contain within 2 standard deviations of the mean? Well, that, my friends, is 95%. Check out this graph. The probability that we're within plus or minus 2 standard deviations of the mean is 95%. Okay, why stop there? Let's go out to 3 standard deviations just to see, right? And that's almost all of our data. 3 standard deviations away from the center. Let's verify in R that the probability Z falls within plus or minus 2 standard deviations of its mean is roughly 95%. Now here's what we want to calculate, the probability that Z is between minus 2 and 2. And to do that, we're going to take the difference of the endpoints. So the probability that Z is less than or equal to 2 minus the probability that Z is less than or equal to negative 2. We do this using p-norm in R. And now remember, if you do p-norm and you don't specify a mean or a standard deviation, it automatically defaults to the standard normal. And here you see p-norm of 2 minus p-norm of negative 2 gets you to that 95%. Now, we could do the same thing for 3 standard deviations. Let's calculate that probability. Here we want to know what's the probability that Z is between minus 3 and 3. Again, it's the difference of the probability of the endpoints, which we plug into R. P-norm of 3 minus P-norm of negative 3 to give us 0.99 or close to 99%. Now, as you might suspect from the formula for the normal density function, it would be extremely difficult and tedious to do that calculation every time we had a new set of parameters from mu and sigma. But fortunately in R makes that process super easy for us, right? Because we can put any data set with any mean or any standard deviation into it. Let's look at an example. Let's suppose X is normal with a mean of 13 and a standard deviation of 4. I want to know what's the probability that X falls within 1 standard deviation of its mean. So here, what are we looking at? Well, we want the probability that X is within 1 standard deviation of its mean. So we've got the mean minus sigma, because we're going down 1 standard deviation, less than or equal to X, less than or equal to the mean plus sigma, because I want to go up 1 standard deviation. Great. When I plug that in, the mean mu minus sigma is 9, mu plus sigma is 17. So I want the probability that X is between 9 and 17. Again, here I'm going to take the probability of the difference of my endpoints. So the probability of that X is less than or equal to 17 minus the probability that X is less than or equal to 9. We do that also with the p-norm function. Notice we can plug in p-norm 17 with a mean equal to 13 and a standard deviation equal to 4 minus p-norm of 9 with a mean of 13 and a standard deviation of 4. And that gives us that 68% probability. Now, we can also solve this problem by standardizing x. Remember, subtracting the mean, dividing by the standard deviation. When we do that, we're always left with a standard normal distribution, centered at 0 with a variance of 1. Here's how we'd standardize that. So instead, again, we want this difference, the probability that x is less than or equal to 17 minus the probability that x is less than or equal to 9. So x minus mu is less than or equal to 17 minus mu minus the probability that x minus mu is less than or equal to 9 minus mu. So all we did here was take our random variable x, subtract out the mean from both sides, right? So x minus the mean, 17 minus the mean. X minus the mean, 9 minus the mean. What do you think we're going to do next? Well, we've subtracted the mean. Our next step is to divide by the standard deviation. When we do that, we get the probability that x minus its mean over sigma is less than or equal to 17 minus the mean over sigma. And we subtract from that the probability that x minus its mean over sigma is less than or equal to 9 minus the mean over sigma. Now, go in and plug in those values, right? We've got 13 and 4 that we can plug in immediately for the mean mu and the sigma equal to 4. And x minus mu over sigma is a standard normal. So that's just a z distribution. So this reduces to the probability that z is less than or equal to 1 minus the probability that z is less than or equal to -1. Again, we get that same probability, 0.68, as we calculated previously. Now, the standard normal distribution has other super useful properties that we're going to use throughout this course. Here are a couple of them. If we want the probability that z is greater than or equal to a, it's the same as the probability that z is less than or equal to -a. And we get this because of symmetry, right? We're centered at 0. So if we go up a and we go down a and look at the tails of those probabilities, they're going to be the same. Another way to write that is this: 1 minus the probability that z is less than or equal to a is equal to the probability that z is less than or equal to -a. And the last property I wanted to show you, the probability that z is greater than or equal to a is 1 minus the probability that z is less than or equal to a. We can see those here on this graph. We can also use R to find percentiles of the normal distribution. So this is the value of A, such that for a given percentage of X distribution, I'm going to lie below that value, right? So the probability that X is less than or equal to some value is equal to A. Say if I wanted to find the 90th percentile for a normal distribution with a mean of 10 and a standard deviation of 5. I want the value of A such that the probability that X is less than or equal to A is equal to that 90th percentile. A couple ways I could find that. Option 1, I could actually do this directly in R using the qnorm command. So if I wanted to find, say, the 90th percentile, I'm going to look for that value of A where the probability that X is less than or equal to A is equal to 90%. I plug that directly into qnorm. Qnorm of 90 with a mean of 10 and a standard deviation of 5. That gives me a value of 16.4. All right, so then what does that mean? Well, that says this. For my normal 10-5 distribution, the probability that X is less than or equal to 16.4 is equal to 90%. Now, option 2, I can actually find the number of standard deviations I am above or below the mean by using the standard normal. And then I can convert it back into X's units. Here's how I do that. I do qnorm of just 90 because the default, remember, is a standard normal. So I'm not going to specify a mean or a standard deviation. And so that gives me 1.28. Now I'm going to take that 1.28, multiply it by sigma, and add mean, mu. So 1.28 times 5 plus 10 gets me right back to approximately 16.4. Now, if the qth percentile of the standard normal distribution is the value A, What do you think is the percentile of the value for negative A? Well, in general, here's what we get. If you've got a qth percentile of a standard normal distribution and it's A, then the percentile for negative A is just 1 minus Q over 100. Remember, we saw earlier that the 90th percentile of the standard normal was approximately 1.28. Well, what's the 10th percentile? Well, we could go into Q norm and calculate it, but we also know we can just take the negative of that value. The 10th percentile is minus 1.28 approximately. Let's do a neat example in R where we look at cholesterol readings for a population. So let's suppose the LDL cholesterol readings in a population are normally distributed. They've got a mean of, say, 129 milligrams per deciliter and a standard deviation of 23 milligrams per deciliter. I don't know how many of you out there have high cholesterol, but if you do, you might want to pay attention to this example. Now, it's recommended that a person consults with their doctor if their cholesterol level goes above 158 milligrams. So let's suppose we take a random person from this population, and we want to know what's the probability that they will have to consult with their doctor. Let's define a couple of things. We're going to set X equal to our cholesterol level. So X follows a normal distribution with a mean of 129 and a standard deviation of 23. So this person is going to need to consult a doctor if their cholesterol level is greater than 158, right? So we're looking for the probability that X is greater than 158. Now again, solving this directly in R makes it easy. You don't need a pencil, you don't need paper. You just go to R and type in P norm of 158. But notice we're not with the standard normal, so we're going to have to specify the mean, 129, and the standard deviation of 23. Notice also we're looking at the probability that X is greater than 158. So we want our lower tail equal to false. This gives us a probability of approximately 10%. So the probability that a randomly selected person is going to need to consult with their doctor is about 10%. Here's another question. What's the cholesterol level below which 95% of this population lies? Right? So now I'm looking at the actual cholesterol level where 95% of my population is below this. We can solve this directly in R with Q norm. Q norm of 0.95, specify the mean, 129, specify the standard deviation, 23, to give us a value of approximately 166.83. Now we can also solve for it using the standard normal. So Q norm of 0.95. And remember here, the default is the standard normal, so we don't have to specify a mean or a standard deviation. We get a value of 1.64 approximately. So to get back to X, we've got to take that value, multiply by sigma, and add mu, which confirms 166.83. Now, many of the things we use around us are actually normally distributed, or at least pretty close to it. I mean, things like experimental measurements or homework grades, even though my students would probably prefer that they not be in the tail end of the homework distribution. But we've seen that the normal distribution is easy to work with mathematically. And in practical cases, the methods that we've developed using normal theory are going to work pretty well, even when our distribution isn't normal. In fact, lots of other distributions can be approximated by the normal distribution, even if they aren't normal. We're especially going to take advantage of this when our sample size starts to increase. In fact, there's a very strong connection between the size of our sample and the extent to which a sampling distribution approaches the normal form. But I want you to be careful because it's not without a pitfall. In fact, a great deal of data actually follows a normal distribution, right? We've talked about lots of things that we know are normally distributed, but some of it isn't. So for example, if you've got data on certain biological phenomena, that's not going to grow according to a normal distribution. It's more likely to be log normal. So normality is going to bring us attractive properties into our analysis, but we always have to be careful that our assumptions are validated.